Welcome to First Principles of Materials and its Science. I am so excited to be kicking this brand new series off with you guys. Think of it kind of like your backstage pass to understand how the stuff that makes up our world actually works. And for our very first deep dive, we are tackling something that you experience every single day, even if you don't realize it: thermal conductivity. Today we're going to break down what thermal conductivity is, why it matters, and explore some pretty amazing examples. You can find more info on the Material Science website. It's linked in the show notes. Now, to help us unpack all of this, I've got an expert on hand with us.
It's great to be here. It's fascinating how we interact with materials that have different thermal conductivities all the time without even thinking about it.
That's so true. Grab a metal spoon and hold it over a candle flame for just a few seconds. You'll feel that heat right away. But try that with a wooden spoon, and it's a completely different story.
Exactly. That difference in how quickly each spoon heats up comes down to its thermal conductivity. Essentially, it's a measure of how efficiently a material can transfer heat energy.
Okay, so it's about how easily heat can flow through something. But how do we actually measure that?
We use a unit called watts per meter Kelvin, or WMK. It tells us how much heat energy, in watts, flows through 1 meter of a material for every degree of temperature difference in Kelvin. The higher the number, the faster the heat flow.
So a material with high thermal conductivity is like a superhighway for heat, while a material with low conductivity is more like a back road.
That's a great analogy. And just like some roads are better suited for high-speed travel, some materials are just built for efficient heat transfer.
So who are the champions in this heat transfer race?
Well, we're talking about the top performers, we have to start with graphene. This stuff is truly remarkable.
I've heard it's like the superstar of material science.
It really is. Graphene boasts a thermal conductivity that's far superior to most other materials. Thanks to its unique atomic structure, it's incredibly efficient at transferring heat energy. Then we have diamond and carbon nanotubes, both of which exhibit exceptional thermal conductivity as well.
It's interesting that those top contenders are all carbon-based.
Yeah.
I always thought metals were the best conductors.
Metals like silver and copper are certainly excellent conductors, and we use them all the time for that reason. However, the way heat is transferred differs between metals and nonmetals. In metals, free electrons carry the heat energy, while in nonmetals like diamond, it's the vibrations between atoms, known as phonons, that dominate the process.
Okay, so the type of material and its internal structure really dictates how efficiently it can move heat around.
Precisely. And this has huge implications for how we design and use materials in everything from everyday objects to cutting-edge technology. Think about your computer for a second. It generates a lot of heat, especially when you're running demanding programs.
Oh, tell me about it. Mine sounds like a jet engine sometimes.
That's why it has a heat sink often made of copper or aluminum, which draws the heat away from the processor.
It's like giving those hot components a cool drink.
Exactly. And speaking of keeping things cool, have you ever noticed how your coffee stays warm longer in a travel mug compared to a regular mug?
Absolutely. That's a lifesaver on busy mornings.
That's because travel mugs are designed with layers of air, which is a poor heat conductor trapped between the inner and outer walls.
So it's not just about the material itself, but also how it's structured.
Right. It's like how a thick winter coat keeps you warm because the fluffy material traps air and prevents your body heat from escaping.
This is making me look at everyday objects in a whole new light.
And the more we understand these principles, the better we can use them to our advantage. For example, diamond's exceptional thermal conductivity makes it ideal for cutting tools.
Diamond. Isn't that a bit extravagant?
It might seem that way, but its ability to withstand intense heat during cutting processes makes it incredibly valuable in industrial applications.
So it's not just about starkle, it's about
Yeah.
performance under pressure.
Exactly. And then we have graphene, which is being used in cutting-edge electronics to manage heat and prevent overheating.
I'm starting to see how understanding thermal conductivity isn't just about science. It's about designing a better world.
Precisely. And this brings us to some really intriguing aspects that might seem counterintuitive at first.
I'm all ears.
For instance, metals, which we generally associate with good conductivity, actually conduct heat better when they're colder.
Wait, really? That seems backwards.
It has to do with how the movement of electrons, those tiny particles carrying heat energy, is affected by temperature changes.
So the colder the metal, the more freely those electrons can zoom around.
That's a simplified way of putting it, but you've got the idea.
And you mentioned something about magnetic fields influencing thermal conductivity.
Yes. It's called the thermal Hall effect.
Okay, that sounds pretty high-tech.
Essentially, when you apply a magnetic field to a material, the flow of heat is deflected.
So it's like you're bending the path of heat with a magnet.
In a way, yes. And this phenomenon has some interesting implications for things like thermoelectric devices, which can convert heat energy into electrical energy.
Wow, that's amazing. It seems like we're only just beginning to understand the full potential of thermal conductivity.
Absolutely. And as we delve deeper into these concepts, we can unlock even more possibilities for technological innovation.
This is all so fascinating. It makes me wonder about the future of materials science.
Well, one area that's particularly exciting is the development of nanomaterials with tailored thermal properties.
I've heard about nanomaterials. They're like tiny building blocks with extraordinary capabilities, right?
Exactly. By manipulating materials at the nanoscale, scientists can create structures with enhanced or even completely new thermal properties.
So it's like fine-tuning the way materials conduct heat at a microscopic level.
Precisely. For instance, researchers have developed carbon nanotubes that act as thermal highways, efficiently channeling heat away from sensitive areas and electronic devices.
It's like building tiny heat management systems right into the materials themselves.
Yeah, that's a great way to think about it. And this has incredible potential for improving the performance and efficiency of everything from smartphones to solar panels.
It seems like we're on the verge of a material science revolution.
Indeed. And as we continue to explore and understand the intricacies of thermal conductivity, we'll undoubtedly unlock even more groundbreaking applications.
I can't wait to see what the future holds. But before we get too far ahead of ourselves, let's take a step back and recap what we've learned so far.
That's a great idea. It's important to solidify the fundamentals before we dive into the more complex concepts. So far, we've journeyed from the basics of what thermal conductivity is to how it plays out in everyday objects and high-tech gear. We've even touched on how factors like temperature and magnetic fields can influence this crucial material property.
It's amazing how something we rarely think about has such a huge impact on the world around us.
Exactly. And that brings us to what I find most exciting, the cutting edge of material science. Because once we understand thermal conductivity deeply, we can start to engineer it, to create materials that do exactly what we need.
That's what I love about this field. It's like having a toolbox for the future.
Yeah.
So what's in this toolbox? What kind of cool stuff are researchers working on?
Well, one material that's been generating a lot of buzz is boron arsenide. It's relatively new on the scene, but some studies suggest it could rival even diamond in its ability to conduct heat.
Diamond is pretty tough to beat. What makes boron arsenide so special?
It's still early days in terms of research, but its unique atomic structure allows for incredibly efficient heat transfer. Imagine the possibilities if we can harness that power, from faster, more efficient electronics to better ways to capture and use waste heat.
It's like we're on the verge of unlocking a whole new level of thermal management. And speaking of unlocking potential, what about those nanomaterials we touched on earlier? Are they living up to the hype?
Absolutely. The ability to manipulate materials at the nanoscale is opening up incredible opportunities for tailoring thermal conductivity. For example, scientists have created carbon nanotubes that act like thermal highways, efficiently channeling heat away from sensitive components in electronics.
So it's like we can build heat management right into the materials themselves. No more bulky heat sinks.
Exactly. And this has implications beyond just electronics. Think about solar panels. By enhancing their thermal conductivity, we could make them more efficient at converting sunlight into energy. Or imagine medical implants that can dissipate heat more effectively, reducing the risk of complications.
It's incredible to think how something as fundamental as thermal conductivity can lead to such groundbreaking advancements.
It truly highlights the interconnectedness of science and engineering. And as we continue to push the boundaries of materials research, we're likely to uncover even more surprising and transformative applications.
This has been such an eye-opening deep dive. Listener, if you're as fascinated by thermal conductivity as we are, don't forget to check out the Material Science website linked in the show notes. There's a whole world of information waiting to be explored.
And remember, the next time you pick up your phone, make a cup of coffee, or even just step outside on a hot day. Take a moment to appreciate the role that thermal conductivity plays in your life. It's a silent force shaping our experiences in ways we often don't even realize.
That's such a great point. It's easy to take these fundamental principles for granted, but they truly underpin so much of our modern world. Thanks for joining us on this incredible journey into the world of thermal conductivity. We'll be back soon with another deep dive into a different topic. Until then, stay curious.